So last time we were discussing the GNSS receiver front end. We talked about the antenna. Antenna is a different part. First we talked about the antenna, then now we are discussing the front end. So under the front end, we talked about the amplifiers and the bandpass filters. And then also we briefly mentioned about the analog to digital conversion at the end. So the output of the front end is digital samples. Today we'll look at the down conversion stage where the gigahertz level carrier frequency is down converted to few megahertz. And in this configuration, this is done in two phases. So at this point, the carrier frequency is gigahertz. We are talking about CA code processing. So in case of GPS, it will be 1.5 gigahertz L1 frequency, carrier frequency. In case of IRNSS, we have L5 and S. So in case of L5, it is 1.175 gigahertz, and for S, it is 2.4 gigahertz roughly. And then at the output, it will be few megahertz depending on the design, few tens of megahertz at this level. And then this will be further down converted to few megahertz here. Now down conversion is performed with the help of an electronic circuit called mixer. Okay. We'll not go into the details of the electronic circuit. Later on the next slide, we'll see how mathematically down conversion happens. But just note that a mixer is an electronic circuit that takes two inputs. Okay, in this case, it is the incoming signal. Okay, after processing, some level of processing, it's the incoming signal, and then the other input is the reference signal. Okay, the receiver generates some reference signal with the help of the reference oscillator and synthesizer, and that is fed to the second input of the mixer. Then at the output, the mixer generates the sum of two signals. Okay, one signal will have a the frequency equal to the sum of the two input frequencies, and the other component will have frequency equal to the difference between the two input frequencies. Okay, so the mixer produces the sum of these two signals. Okay, which is again passed through a bandpass filter. Now I should note that in case of down conversion, always mixing is preceded by a bandpass filter. Here we see the amplitude of the bandpass filter. It passes a band of frequencies centered around the center frequency. So in case the center frequency, in this case the center frequency is the carrier frequency, because this is the first stage of down conversion. But here the center frequency will be the down converted frequency. Okay, so mixing is always preceded by a bandpass filter and followed by a bandpass filter. On the next slide, we'll understand why this is so. Before going into the mathematical operation of mixing, we need to represent the signal at the receiver level. We saw a mathematical model of the signal at the transmitter level when we talked about the signal structure. Now let's represent the signal from a satellite at the receiver level. It's given by again S of t, but this time t represents the time of reception. In the earlier mathematical model, t was time of transmission, the time at which the signal started from the satellite. But at this point, t is the time of reception, it is the time at which the signal is received by the receiver. Then this term is the P is power. P is received power now. This is not the same as the transmitted power. Then C is the code, D is navigation data, T is time of reception, TTR is the travel time, signal travel time, the time that the signal requires to reach the receiver after it started from the satellite. So TTR is the travel time. So when we subtract the travel time from the time of reception, we basically get the time of transmission. But since code and data were transmitted by the satellite, we should have the time of transmission as the argument. That's why TTR is subtracted from T for both code and data. Then the carrier component comes. We are considering the SPS signal structure, the simplest one, which is modulated by code and in legacy nav data for CA code and legacy nav data for GPS. And in case of IRNSS also, we have a variant of CA code and then the corresponding nav data for IRNSS. The quadrature phase component, which is available to everyone, has cos. We can also represent it as sine, but then theta naught will be different. But we generally use cos representation. So cos 2 pi FL, FL is the carrier frequency, and then theta naught is some initial phase offset. What was not present in the earlier signals structure was this component, FD. FD is the Doppler frequency. Because of the relative position between the satellite and the receiver, this Doppler component arises, and in a previous class we also derived the expression for the Doppler. It is given by this. FL is the transmitted frequency. In the L1 band for GPS it is 1.575 gigahertz. For IRNSS, as I said, 1.175 for L5, and for S 2.4 gigahertz. C is the speed of light, Vs is the satellite velocity vector, U is the user velocity, this is the dot product, and U is the line of sight vector, the unit vector along the line of sight from user to satellite, that is U. So you derive this expression in the class, will not go into this again. So this is the expression of the Doppler, and in the received signal this Doppler component gets added to the transmitted frequency. So the received frequency is the transmitted frequency plus Doppler. And then of course noise is present. While receiving the signal, some noise will also be received. So that is represented by this italicized N here. So this will also be italicized, the same notation. So it represents noise. Okay. So this is the signal structure that we are going to consider in our subsequent discussion. It is the signal received from a satellite at the receiver level. Now let's see how mixing or down conversion is performed. So the mixer mathematically multiplies this one. Okay, so this is actually one of the, so this S of t is coming here, and the other one, the second input is this, which is electronically multiplied to this one. So we have cos here, we have cos here. And you see the argument, it is 2 pi FL minus FI F1. So after the first stage of down conversion, let's say the frequency is FI F1, IF stands for intermediate frequency, and then some offset will be there. So when we multiply two cos terms, we know that if this is cos A and this is cos B, then we know that we will get at the output we will get two terms, right? One will be cos A plus B, another will be cos A minus B. So what will be cos A plus B? This will just give some offset. So let's consider the first term in the argument, cos A plus B. So if we do cos A plus B, we have 2 pi FL, which is of the order of few gigahertz. And then it will be multiplied by 2 because we are adding these two terms. And then FD will come minus FI will come. So the first component, cos A plus B term, will give a frequency twice the carrier frequency. How about cos A minus B? Cos A minus B will actually cancel out the FI. Because here also we have 2 pi FL, here also we have 2 pi FL. So 2 pi FL will cancel out, and we'll have FIF1, 2 pi FIF1 plus FD. So that is the cos A minus B. Now we can clearly see that one is high frequency component, cos A plus B is the high frequency component, and cos A minus B is the low frequency component. We do not want that high frequency component. we want to change FL to FIF1, and the second term, the low frequency component, A minus B term, has FIF1, FL is cancelled out, plus FD. So you want that term only. You want the low frequency term. You do not want the high frequency term. The high frequency component is filtered out by the subsequent BPF. This BPF, band pass filter, which follows the mixer, filters out the high frequency component and allows only the low frequency component. So at this point, we have the down converted low frequency component where the carrier frequency is down converted to the first intermediate frequency FIF1. Then in the second stage, again the same thing will happen, and finally we get the final intermediate frequency. Let's call that FIF. Okay. Now we understand why we have a band pass filter after mixing, but why do we require a band pass filter before mixing? One reason is that following an amplifier, we should always have a band pass filter, because amplifier, in addition to amplifying the signal power, introduces noise and some unwanted signals, which should be removed using the band pass filter with the help of suitable design. This is one reason. Another reason is as follows. Now suppose in the incoming signal, we not only have this one, we also have some unwanted signals. For example, suppose we have an unwanted signal picked up by the antenna with this cos term. Pay attention to the argument, cos 2 pi FL minus 2 FIF1. This is not a desirable cos term. We do not want this. But what happens to this component after down conversion? So in place of this, now you just consider this one and do the same thing. So this is A, cos A, and this is cos B. A plus B will again give you the high frequency component. So 2FL will come, which will be eventually filtered out by the band pass filter. But how about the low frequency component, A minus B term? FL will cancel out, and we have minus 2F IF1 here, and here we have FIF1. So if we subtract this from this, we actually have in the low frequency component we have cos 2 pi minus FIF1. So minus 2FIF1 will come from the A term, and then we are subtracting B, so plus FIF1. So eventually we have cos minus 2 pi FIF1, which is equal to cos 2 pi FIF1. Now this component, the low frequency component, is within the passband of the band pass filter. So the band pass filter will allow it. So wrong component is allowed. We do not want this. Now these types of frequencies which move to the passband of the subsequent band pass filter after down conversion are called image frequencies. Now we do not want image frequencies to be passed. So the preceding band pass filter is designed in such a way, and the intermediate frequency is chosen in such a way that this filter removes such image frequencies. So with the help of the preceding band pass filter, we remove image frequencies, and with the help of the following band pass filter, we remove high frequency components. We allow only the desired low frequency component. So this is why always mixing is preceded by a filter and followed by a filter, band pass filter. Okay, that's all about mixing. Next, after down conversion, analog to digital conversion takes place. So here we have, at the end we have an analog to digital converter, which finally converts the analog signal into digital samples. So after A to D conversion, we have samples like this. Tk is a time instant, particular time instant, S of Tk. And the same thing I have written, but in terms of Tk. So this is the sample Sk at time Tk. Okay, everything has been written the same except for T. So in place of T, we have now Tk. Okay, now this N and this italicized N, they are not exactly the same. That's why I have used subtly different notations. Okay, so this is the final noise sample at the digital part. So this is the output that we get from the front end. Subsequent processing takes place with digital samples. The next component after the front end is the baseband signal processor. Now don't feel intimidated by this block diagram. It is quite simple. I am going to explain each component in simple words. So do not get intimidated by this block diagram. The next component after the front end is called the baseband signal processor. So what does the baseband signal processor do? First of all, after front end, everything is in the digital domain. So digital signal processing begins. And from this point onwards, we have different channels for different satellites, meaning each satellite will be processed separately. So there are 12 satellites visible for GPS alone. There should be at least 12 channels in the receiver, 12 separate legs. Channels, you can think of legs, okay? Separate legs. Here you see the baseband part for a particular channel. So if there are 12 satellites, there will be 12 such channels. The parallel processing will take place. Modern receivers have capability of processing hundreds of channels. Okay. A multi-constellation receiver should be able to process hundreds of channels. For example, some of you had shown on the Skyplot, GPS, GLONASS, Beidou, for QZSS. So those receivers should have at least 100 channel running together. Okay. Here we just see the baseband component for one particular channel. Now what is happening here? So we had the digital samples from the front end. S of k for different instance of time are coming from the front end. This notation is for mixing. Okay, again here mixing takes place the same way as we did in case of down conversion, but the objective is different. So one input and this also is in the digital domain. Okay, so one input to the mixer is the digital samples, and it is divided into two legs now. The digital samples go to two legs, two parallel legs. Okay, now the other input is generated by the receiver. This is called the replica carrier. You see, cos 2 pi FIF, it is the down converted carrier. In place of FD, we have FD hat. The receiver's knowledge of FD. FD hat is the receiver's estimate or receiver knowledge of the Doppler frequency times Tk plus some offset. The cos term gives this one to this leg, and then the sine equivalent. So in place of cos in this block, we have sine of the same thing is fed to this leg. Now the leg which has cos term is called in phase I, and the leg which has sine coming from this side is called quadrature phase. In phase and quadrature phase, I and Q. What happens here? So we are multiplying two cos. Here we have cos, and then we are multiplying another cos. Here we have cos and sine we are multiplying. So again we get two components. This simple mathematics. We are multiplying two cos terms or one cos, one sine term. We will get two frequency components. One will be high frequency component A plus B. Another will be low frequency component A minus B. Now we are not bothered about the high frequency component because it can be shown that subsequent operations, for example summing up, will eventually remove the high frequency component. So you are not bothered about the high frequency component. We are interested only in the low frequency component. Now A minus B term both have FIF. In the incoming signal after down conversion we have FIF plus FD, and here we have FIF plus FD hat. FD hat and FD need not be the same. The receiver's knowledge of FD is FD hat. So if you do A minus B, which is the low frequency component, IF is removed. What you get is FD minus FD hat. The Doppler error. This is the Doppler error. So this is for the in-phase leg, which we call I carrier. Similarly, if you do the math for cos and sine, for the quadrature phase, you will get a sine term. A noise will be changed accordingly. That's why I put NI and NQ. So at the output, we get I carrier and Q carrier. Now pay attention to this term carefully. What are we doing here? We do not have any carrier component. Down converted carrier is removed. That's why this phase is called carrier wipe off. By doing such mixing operation, we remove the carrier, because in the final expressions of I and Q, we do not have any carrier component here. We just have the Doppler. Okay, and the initial phase offset is also adjusted accordingly. Here we call theta IF, theta IF. So this phase is called carrier wipe off because we remove the carrier by doing this operation, mixing operation. Don't worry about this block, carrier NCO. I'll explain this to you in another presentation, not today, maybe tomorrow or day after tomorrow. After carrier wipe off, the next stage is called code wipe off. How and why? So in case of code wipe off, we actually multiply the replica codes. I told you many times in previous lectures that the receiver generates replica codes. And there are three types of replica codes generated: early, prompt, and late. Why three codes? I will explain again. I already explained once, but I will explain again in the next slide. Just note that three, in case you do not recall it, note that three different replica codes are generated internally by the receiver. They are called early, prompt, and late codes. Since everything is in digital domain, we are dealing with samples. Here also samples of the code are generated. And then each of the three codes samples is multiplied with this I leg and Q leg separately. So you already have one pair at this point. Now each pair is multiplied with three different code samples. So we basically have 6 legs at this point, meaning 3 pairs. So when these 2 legs are multiplied with E code samples, early code samples, we get these pairs. When they are multiplied with P, we get this pair. When they are multiplied with late code samples, we get this pair. So multiplying means we again multiply. In the digital domain, we multiply them. Since mixing does multiplication, we have the same notation, same symbol here. Okay, we are doing multiplication, sample by sample multiplication. Incoming sample and the code samples, they are multiplied at this point. And since there are 2 legs for each, we get 1 pair. There are 3 of them, so we get 3 pairs. Okay. Now when we multiply this P code, that is the code that the receiver wants to align with the incoming code. Now suppose an ideal situation is there and the receiver has been able to perfectly align the prompt code with the incoming code. Then these prompt code samples are multiplied. So you can imagine some C hat here multiplied. We know that C takes one of the two values, plus or minus 1. You multiply C hat to it. C hat is perfectly aligned with C, meaning it will also take, if C takes plus 1, C hat will also take plus 1. If C takes minus 1, C hat will also take minus 1. So after multiplying C hat, when prompt is perfectly aligned with the incoming, you actually remove this C term, because plus 1 plus 1 if you multiply you get plus 1. Minus 1 if you multiply you will get plus 1 only. Right? So by multiplying the prompt code samples, when it is perfectly aligned with the incoming, you actually remove the code by doing this operation. This is why this phase is called code wipe-off, because you are stripping off the code. Here the carrier was removed. Here the code is removed. If prompt, of course in the prompt leg here, if prompt is perfectly aligned with the incoming code, and the objective, one of the objectives of the receiver is to perfectly align the prompt code with the incoming. This is why this phase is called code wipe-off. Okay, now what we are doing here, we are multiplying the samples, and then this notation is for summation. We sum up all the samples over this interval, coherent integration time, T coherent. Okay. In case of this SPS signal, which we are considering here, T coherent varies from 1 millisecond to 20 milliseconds. The duration of the data bit in case of the signal structure that we have considered here is 20 milliseconds. 50 bits per second means each bit is 20 millisecond long. At this point, while doing the summation, we do not go beyond a data bit interval of 20 milliseconds. So T coherent generally takes values from 1 millisecond to 20 millisecond. Okay. Now this is the case for the signal, the simplest signal that we have considered in our discussion. Don't think that it always has these values from 1 millisecond to 20 millisecond, any value. No, it can be more than that. Okay. But for the signal structure we have considered here, it varies between 1 and 20 millisecond. Okay. Now let's see why we have early, prompt and late again. We discussed this, but let's discuss this again because understanding this is very important. Early, prompt and late. Why do we have 3 different replica codes generated inside the receiver? Now for this purpose, let's consider the correlation, autocorrelation, the primary peak of the autocorrelation function. This is the primary peak of the autocorrelation function after some approximation. And we also discussed the mathematical function for it. This is the mathematical function 1 minus mod tau. Tau is the code phase alignment error by TC. This has a value within plus minus TC. Outside that range, it is 0. R is the notation that we will use for the autocorrelation function in our subsequent discussion. Now tau, the code phase alignment error, can be in seconds. Then this TC is the chip width, the duration of a chip. If TC is in seconds, In case of CA code, there are 1.023 into 10 to the power 6 chips in a second. So 1 divided by 1.023 into 10 to the power 6 will give the chip duration, which is TC. Now if you represent TC in seconds here, this also has to be in seconds. If you represent TC in chips, then TC is equal to 1. Tau will also be in chips. So we can have this representation either in seconds or in chips. TC will be modified appropriately. TC should be in seconds if you want it in seconds. Here, TC should be in chips if you want it to be in chips. When you express it in chips, TC is equal to 1 chip. You already discussed this. I am just quickly saying this again. Okay, so this is the autocorrelation function. Now let's see why we have early, prompt and late again. Let's assume that this is the incoming chip, some chip in the incoming signal at some point in time. Let's say this is the current time instant. Time is progressing in this direction. So this side, whatever appears, that has already passed. Whatever is yet to come is this side on the right side. Whatever has already passed is on the left side. And let's say this is the current time instant. The midpoint of some chip in the incoming signal is there at the current time instant. The objective of the receiver is to align the prompt replica with the incoming. So let's assume an ideal scenario where the prompt is perfectly aligned with the incoming. So this is the corresponding prompt replica generated by the receiver, the green. What is code phase? CP stands for code phase. We define code phase many times in the class. What is code phase? Code phase is the beginning of the current. So let's say the code period begins at some instant and we have 1023 chips in a code period. So we are interested in finding the code phase, which will be the number of chips preceding the current chip and the fraction of the current chip up to the current point. This is the code phase CP, incoming code phase. Now we need to do the same for the prompt. From the beginning of the current code epoch or code period, we need to find the number of chips preceding the current chip and the fraction of the current chip up to the current point. So this will be CP hat, the prompt code phase. Now when prompt is perfectly aligned with the incoming chip, both are the same, the code phase alignment error tau is 0. If tau is 0 here, then we get R. So it will be here. The maximum value of the autocorrelation peak is obtained when tau is 0. How about replica and late? Early and late. Early is shifted ahead of prompt by this amount, D times TC by 2. When you express TC in chips, this will be 1, TC is 1, so D by 2 chips. And late is shifted behind the prompt by the same amount, D by 2 chips. Now, as I said, anything on the left side has already passed, anything on the right side is yet to come. So in case of early, since it is shifted ahead, the midpoint has already passed. For the early at the current point, this point is there. Whereas for late, the midpoint is yet to come because the late is shifted behind the prompt. So it is yet to come for late. How about the code phase errors for early and late? So early code phase will be CP hat, the prompt code phase. Since it is shifted ahead by this amount, you need to add this DC by 2. And how about the code phase error? So CP minus CP hat will be there. That will give tau plus this term, minus this term. So you have to to get the corresponding code phase, you have to subtract this whole thing from the incoming code phase Cp. So Cp minus Cp hat will be tau, and then this will become minus. So we have minus dC2 by Tc by 2. This is the early code phase error. How about the late? In case of late, the same thing you will do, but here we have negative because late is shifted behind. So it is minus dTc by 2. So this will become plus tau plus dTc by 2. So this is the late code phase error. Now what happens when we correlate? We discuss correlation. What happens when we correlate? Here what are we doing? We are actually multiplying the code samples to this I and Q terms. Let's assume that receiver's knowledge of FD is very good. So this is very small. This is also small. So this term is very small. So this can be approximated as 1. Whereas this is very small. And we are multiplying the code samples here. So eventually what we are doing, and then we are summing them up. Eventually we are doing correlation. Summing up is equivalent to integration. So we are doing correlation here. Let's assume for simplicity T coherent is 1 millisecond. 1 millisecond is the code period, the duration of the C code. And for when talking about autocorrelation and cross correlation, we consider the integration over a code period. So this whole thing, this one and this one together is basically correlation. Right? So we are doing correlation, correlating the prompt in these legs, correlating the early here, correlating the late here. And we already know how the correlation function looks. When the prompt is perfectly aligned after correlation, it will be here. Tau is 0, so we get this. When early is correlated, the corresponding correlation value will be here. When late is correlated, the corresponding value is here. So for the in-phase leg, this is the in-phase leg, we are actually getting this for prompt, for early this one, for late this one at this point. For the quadrature phase, this is very small, so we are not considering the quadrature phase at this point. Why do you want this? See, when the prompt is aligned with the incoming, both early and late, they have the same value. What if the prompt is not aligned? Let's say the prompt midpoint is yet to come. It is not perfectly aligned, so it will come here. So this much is the error. The corresponding correlation, because tau is not 0 now, tau has some non-zero value, so it will be less than 1, so it will come here. This green point here will be shifted down here. What will happen to red and blue? They will also be shifted. Red will be shifted up, blue will be shifted down. So when the prompt is not aligned with the incoming, early and late correlation values are not the same. So by comparing early and late correlation values, we can align the prompt with the incoming. So the objective is to design some feedback control loop where we need to do the comparison between early and late and try to zero the error between them, so that the prompt is aligned with the incoming and the green point in the correlation peak is here. This is the objective. And a feedback control loop is designed using the baseband signal processor and the subsequent ranging processor. Here we are just seeing some components of that feedback control loop. When we talk about the ranging processor, it will be completed and we'll have an equivalent block diagram representation under some assumptions. Okay. Now D has a name, okay. D is called early and late correlator spacing. So the early is shifted ahead of prompt by D by 2 chips. Late is shifted behind the prompt by D by 2 chips. What is the separation between early and late? It is D. That's why D is the early and late correlator spacing. A typical value of D is 1. That's why I have shown the midpoints this way. Typical value is 1. Okay. When D is less than 1, we call narrow spacing. Here it is shown D is less than 1. When D is more than 1, we have wide spacing. Narrow spacing and wide spacing. Any question up to this? Understanding this is important. So if you do not understand, if you want me to repeat, ask me. If you do not ask me, I'll move on to the next slide. I assume you have no questions and I move on to the next slide. But if you do not understand, you will not be able to answer anything. For example, if I ask you why 3 replica codes are generated, if you do not understand what I said, you will not be able to answer. Okay, I assume you have understood, and with that, I'll move on. So we understand that at this point, carrier is wiped off. We have removed the FIF, intermediate frequency. Here, if prompt is aligned with the incoming, code can also be wiped off for the prompt leads. That's why the name is code wipe off. Now we are interested in the mathematical expressions of these terms, which are fed to the subsequent ranging process. So the next block where these are fed, this I and Q pairs are fed, is called the ranging processor, which we will discuss tomorrow. Okay. Now let's see the mathematical expression of I and Q. We'll not do the derivation. In offline classes, I do the derivation, but in online classes, since things go slowly, it's not possible to do the derivation, but I'll quickly explain to you why we got these different components here without going into detail of the mathematics. Okay, so this term is from the incoming signal, the power, signal power term. This remains as it is. I'll come to capital M later. This is the data bit, D. I said that the coherent integration time T coherent for the signals we have considered here varies from 1 millisecond to 20 millisecond. So it will be either 1 millisecond or 2 millisecond, or it can be 5 millisecond. There are some specific values that we generally consider. 1, 2, 5, 10 and 20. Okay. Now D is, one data bit is 20 millisecond long. Within this 20 millisecond, within a data bit, D does not change sign. The sign of D can change only after 20 milliseconds. Okay. So generally if T coherent is within 20 milliseconds, it can be expected that D does not change its sign. We know D can take one of the two values, +1 or -1. So if we restrict T coherent within 20 milliseconds, there is a higher chance that D will not change its sign. So we assume that D has the same sign over this summation interval T coherent. So it does not change. If D changes sign, then this will introduce error. Okay, so we'll not get into that. We assume that within this summation interval, which is called the coherent integration time, D does not change its sign, so it remains the same as it is in the incoming signal samples, and therefore we take it as it is. This is not changed. Okay. Then on the previous two slides, we discussed that this is equivalent to correlation. We assume that FD hat is close to FD, and then we assume that the cost term is almost equivalent to 1. So you are multiplying the code samples, average, summing, that is equivalent to integration. So you are basically doing correlation. That's why this correlation term comes R. For prompt, it is tau, R of tau. Tau is the prompt code phase error. Prompt code phase error. How about this delta term? Now here, see, this expression can be used for early, for prompt, or for late. But delta here will change its value accordingly. If you consider it for prompt, delta is 0. Okay, because the code phase error here is just tau. If you consider the early pair, then the code phase error is tau minus dTc by 2. The same has to be written here, tau minus dTc by 2. So delta is minus d by 2 for early. If you consider late pair, then it is tau plus dTc by 2. So this will be tau plus dTc by 2. So for the late pair, we have to consider delta as d by 2. Okay. Now how about these terms? Now see, while explaining the correlation, we ignored this. We said that FD hat is almost equal to FD, and therefore this term is equal to 1, and this is very small. But they will not be equal, right? They are most equal. They will not be exactly same. Therefore, some contribution will come when we do this operation from the cos and sine term, right? In the digital domain, summation is equivalent to integration. So we can mathematically integrate the whole thing, okay? And then finally we'll see that after doing integration, we get these extra terms because of cos and sine. It can be shown, okay? So this is for the in-phase leg. For the quadrature phase leg Q, we have the same sign. This is basically a sinc function. Sinc function. While talking about the code spectrum, the Fourier transform of code, we talked about the sinc function. I'm referring to the same sinc function. For the in phase, we have cos delta phi. For the quadrature phase, we will get sine. Okay, and then equivalent noise terms will also come. What is delta phi? Delta phi is the carrier phase error. What do we mean by carrier phase error? See, the incoming carrier is a sinusoidal function. The replica carrier is also sinusoidal, replica and incoming. So each will have its phase, right? This is the replica carrier. Similarly, this is the incoming. So at some time instant it has a phase, correct? Similarly, the replica also has a phase. The difference between two carrier phases at the beginning of this summation is delta phi. So if the replica carrier is perfectly aligned with the incoming carrier, delta phi will be 0. What is delta FT? Delta FT is the Doppler error. This is the incoming Doppler, the Doppler frequency present in the incoming signal, and FD hat is the receiver's knowledge of Doppler, receiver estimate of Doppler. The difference between the two is the Doppler error. So this delta FD term comes here. Next is M. M is the number of samples summed. Imagine a particular configuration where the sampling frequency is 5 megahertz. Meaning, how many samples do we have? 5 into 10 to the power 6 samples we have in a second. Coherent integration time is of the order of 1 millisecond to 20 milliseconds. So in a millisecond, how many samples will be there? If 5 megahertz is the sampling frequency, 5 into 10 to the power 6 into 1 millisecond, 10 to the power minus 3. So 5,000 samples will be there, 5,000 will be multiplied. If T coherent is taken as 20 millisecond, 5,000 into 20 will be multiplied here. This is a big term. This has an important implication. While talking about the front end, I mentioned that signal is very weak. Signal power is below the noise power. You cannot separately identify the signal. Now here, this is the signal component. This is coming from the signal. This is noise. You have a large multiplier in the beginning. 1 millisecond, 5,000 is multiplied. The same does not happen for noise, okay? 20 millisecond, 5,000 into 20 is multiplied. So by doing this correlation, signal is amplified over noise. So at this point, we can identify the signal from noise because signal is amplified over noise. In front end, both signal and noise are amplified together. We have a number of power amplifiers in the front end. Both signal and noise are amplified there. We cannot separate signal from noise. But at this point, by intelligently designing the operations, we might amplify signal over noise. Okay, so here signal is amplified over noise. The objective of the receiver is to basically make this tau 0. In other words, to align the prompt with the incoming code. And it does this with the help of a feedback control loop called code phase tracking loop. We'll come to this tomorrow. We'll discuss this tomorrow and day after tomorrow. So with the help of a feedback control loop, the receiver zeros this, tries to zero this tau. And the corresponding loop is called the code phase tracking loop. Okay, then with the help of another feedback control loop, the receiver tries to zero the carrier phase error, meaning it tries to align the replica carrier with the incoming carrier. And that loop is called carrier phase tracking loop. Now, phase tracking is not possible without zeroing Doppler. So, if delta phi is made 0, eventually Doppler also has to be 0. Without making Doppler 0, you cannot have 0 carrier phase error. So, if the receiver tries to zero delta phi, automatically delta FD will be made 0. I mean, it will be close to 0. But it is not always possible to make delta phi 0, okay? For example, if C over N naught is not good, if the vehicle on which the receiver is mounted is moving fast, changing its orientation fast, then making delta phi 0 is not always possible. Under such circumstances, an alternative is to make delta FD 0. The corresponding feedback control loop is called carrier frequency tracking loop. Then delta phi will not be 0, but delta FD will be close to 0. So the code phase tracking loop runs, and either the carrier phase tracking loop or carrier frequency tracking loop runs. Okay. Now, why we want these loops? Why do we want to zero the errors? If this is 0, this term vanishes, it is 1, when it becomes 1. If delta ft is 0, this also becomes 1, sinc function, this becomes 1. Consider the prompt, so delta is 0, if tau is 0, this becomes 1. So everything becomes 1. This term is much more dominant than this one, so we can ignore this. So what do we have here? We just have D. So from the sign of IP, we can find the data bit. We can demodulate the data. Okay, we'll continue tomorrow. Any question? Anything that you are not following, you should ask me at this point.